Good afternoon. Please welcome Mark Jessop and Michael Wheeler talking about STM32 development boards, literally falling from the sky.
Hi everyone, I'm Mark Jessop. My amateur radio call sign is a VK5QR. I'm from Adelaide.
And I'm Michael Wheeler, and my call sign is VK3FUR, and I'm from Melbourne. So today we're going to have a sort of quick overview as to what a weather balloon is and what a radiosonde is. A little bit of a sort of primer as to how they operate, what they are, what they do. We're going to look at a specific radiosonde, the RS41, and that's because we want to sort of repurpose them, make use of them, find them. Part of that is the Radiosonde AutoRX project that Mark has put a lot of effort in, and it's designed around finding them. And finally, we want to look at recycling the radiosondes. So that means going out, finding them, bringing them back, and then repurposing them for some other purpose.
Live demo number 1. Let's see how we go. Okay, if you haven't seen this website, this is awesome. This is called earth.nullschool.net. This is a visualization of the global forecast system. So this is a weather model which covers the entire Earth. It's a predictive model. It covers about a week ahead from the US National Weather Service. Now, things that are interesting on this model, particularly to this talk, currently we are seeing a visualization of wind speed and direction. The brighter colors, the hotter colors, sorry, represent higher wind speeds. And the most important point of this is if we look at the wind speeds and directions as we go up in altitude, they're not consistent. So in meteorology, altitude is determined through pressure altitude. That's because the bulk of the Earth's air is not uniform, and a particular pressure may not equal a particular altitude at the same point around the Earth. So at surface level, we can see, okay, we're getting calm winds over New Zealand at the moment, but you know, fine. We go up in altitude, so 500 HPA is something like 5 kilometers or so. Higher wind speeds, different directions. As we go higher still, even higher wind speeds. And at 10 HPA, which is about 25 kilometers, it's going in entirely different direction. It's now coming from the east. Now, the global forecast system depends upon inputs to work. We need temperature, humidity, pressure, and of course wind speed and direction. Now, a lot of this information comes from ground-based weather stations, scattered all around the world. But to provide truth data for these higher altitudes, we have to have direct measurements at these altitudes. This is where radiosondes come in. Right. Oops, wrong way.
So Mark is holding up a lovely RS41 radiosonde, and on it we have some sensors. So we have temperature and humidity on some special radiosondes, not this specific one. We also have pressure sensors. There's also potential for what they call an ozone sonde, which is a sort of styrofoam box that would attach to this, and that measures the ozone as it goes up through the sky. Typically you have a radio signal that downlinks all the data. In Australia and New Zealand, that's somewhere between 400 and 406 megahertz. In the US, it's a little bit higher at 1.6 gigahertz. Inside the radiosonde is also a GPS transmitter, and that's what we use to work out where the radiosonde is, so we can work out what the wind speed is. So a few sites around the world launch radiosondes.
Hang on. Oh, not quite. All good. So the particular radiosonde we're talking about itself, the RS41, made by a company called Vaisala. They've been doing this for a long, long time. In fact, they developed the world's first radiosonde in 1930. So a box quite a bit larger than this. Again, think how big computers were back then. They use valves, so yeah, a bit big. But they've gotten better. They have a massive chunk of the worldwide radiosonde market. They're not quite a monopoly provider, but not far off it. Unlike their previous radiosonde offerings, which had a whole lot of custom silicon in them, and I do mean custom silicon, it was nuts what they used to do, this uses commodity components. So things that we can work with, we can get data sheets for, we can reuse. So the anatomy of an RS41. First up, we have a microcontroller, STM32 F100. So commodity microcontroller, it's their value line, so it's a bit small. 64K of flash and 8K of RAM, so not particularly big. Read protection is turned on, so no dumping of firmware just yet, but it might happen. It also has a GPS receiver. So this is a U-Blox 6 GPS chipset. These are a very common GPS receiver and very high quality as well. A little tiny chip antenna on the left-hand side of the PCB, very easy to talk to, serial connection. If you want to, you can cut some traces, wire in a USB to serial adapter, and voila, you've got your own GPS receiver. This particular chip, the U-Blox 6, is not far off being obsolete. So given that Vaisala are going to continue manufacturing these particular sondes for many years to come, I'm interested to see whether they update to the most recent U-Blox 8 series, which has much better performance. There's also a radio transmitter. It's a fairly old chip. It's by a company called Silicon Laboratories. It transmits frequency shift keying. And now the cool thing about this chip is that it is incredibly frequency agile. It'll work anywhere between 240 and 930 megahertz. Now the board is designed for the 400 megahertz Radiosonde band. However, it works pretty well in the amateur radio 430 megahertz band, which is where we want to use it. The silver flexible PCB on the top left-hand corner there is where Vaisala's secret sauce lives. So Vaisala are a meteorological sensor company. They make temperature and humidity sensors, and they do it good. This temperature sensor is good from positive 60 to negative 90 degrees with 0.3 degrees of uncertainty. It's incredibly good. There's a humidity sensor which covers 0 to 100% humidity, fine. Unfortunately, we don't know how to use either of them in our own code. Vaisala have implemented their own analog to digital converter on the PCB. Yeah, my analog knowledge kind of fell out of one ear a few years ago. I haven't quite figured out how to drive it yet. Last but not least, we have a couple of external interfaces. There's a 10-pin expansion header, which is where things like those ozone sensors might plug in. And there's also this weird little coil on the board, which is actually used to program the sonde, at least set the frequency prior to launch, and run a few calibration routines as well. So to get these radiosondes up into the upper atmosphere, we use weather balloons. It's pretty obvious. Large latex balloons, they do biodegrade. The plastic of the sonde, not so much. They might be about 1 meter or 2 in diameter on the ground. Once they reach higher altitudes, they're about 5 meters across, then they burst and fall back to the ground. The target altitude for most radiosonde flights is about 28 kilometers above the Earth. And I'm pretty sure all the Australian radiosonde launch locations currently use hydrogen as a lifting gas. Now note the sign beneath the balloon and the lack of people around it. This is because hydrogen burns. Again, just by itself, it's actually pretty safe. Now, while hydrogen is somewhat dangerous, they use it because it's cheap. They can actually generate it on site if they choose to. And because helium is a scarce resource that people like me use to send stuffed penguins into near space. Who was at LCA 2011? Right, yeah, it's Tux in near space. So this is a terrible graph, I'm so sorry, but it gives some idea of the raw data that we might get out of a radiosonde launch. In this case, this is from, I'm not going to butcher the name, it's just north of Wellington, and we can see we have temperature, dew point, wind speed and direction from ground level, in this case up to about 16,000 feet altitude. In fact, the sonde went a lot higher than that, but this particular plot is targeted at glider pilots, who only really, if they're up at 16,000 feet, they're probably doing something wrong. You can get this data for free, not from the Bureau of Meteorologies, those various organisations, because they don't seem to publish it easily. However, Mark Newton, who now works at Google, has an awesome website, slash.at.org, where you can get all this data for free for the Australia and New Zealand regions.
So across Australia and New Zealand, there are many, many launch sites. A lot of these are major airports. Typically, the Bureau will have a little site on the airport they can launch the balloons from. Some of these sites are also completely automated. There's an automatic radiosonde launcher that will launch these balloons. Thanks to the BOM, they've been able to give us some of this data as to where a lot of these launch sites are. So we were able to plot this on a map for you to look here. Some of these sites will launch 2 times a day. Other sites will launch maybe 2 times a week. So if you're curious and want to try and find a Radiosonde, if you want to come see us after the talk, we can look up your particular launch site. But the general gist of things is you're going to be maybe 1 to 2 hours drive away from a Radiosonde launch site. So I think it's pretty open for most people to be able to play around with this. So as I said before, we got 2 launches a day for most places. They launch at around 11:15 UTC and 23:15 UTC. The reason for this is they want the balloon to sort of be at that peak altitude at roughly midnight or midday UTC, so that they can generate a weather model across the world that is using the same sort of time for their data. So the ascent is about 1.5 hours long, and it's during the ascent it's about 5 meters per second, the balloon moving. It bursts at 27 Ks. Sometimes different launch sites will have sort of a different average altitude, but it's roughly around there. It will land about 30 minutes later, and the Radiosonde will transmit for another sort of 6 hours. One key thing is when it descends, it will descend at a completely different rate. So it could descend at like 7.5 meters per second is what we sort of roughly see, but it will depend if it has a parachute, doesn't have a parachute, a radar reflector, that sort of stuff. So there's lots of variables to sort of take into account. Sort of when it's ascending, it will be going at one rate, which means it will spend a certain amount of time in different winds. And when it comes down, it'll come down through different winds at different rates. So you'll get sort of an asymmetric path that will follow through the sky. This gives us a chance to recover it because it keeps on transmitting for 6 hours.
Right, so the Radiosonde AutoRX project, track all the Radiosondes. I had to use the meme, I'm sorry. So we originally developed this because the Radiosonde transmission frequencies in Australia were very inconsistent. In Europe, where there are many different agencies launching these balloons, they are all coordinated. They know exactly what frequency each launch site's going to transmit on ahead of time. You know, you can just pick a frequency and you know what's going on. In Australia, they just kind of do their own thing. It is all the Bureau of Meteorology. Each of the launch sites would pick a random frequency, essentially, within that Radiosonde frequency range. We had to have a way of scanning the Radiosonde band to find the frequency and then decode them. So at the core of AutoRX is some demodulator code written by a guy called Zilog80. He spent a long time doing reverse engineering of the telemetry formats that these things transmit. Vaisala are completely closed about this entire system. They don't publish any information about telemetry. As you know, worldwide monopoly, right? It makes sense for them. So we've pretty much wrapped this in Python to automate it and decode things automatically. We currently support Radiosondes from Vaisala, so the RS41 and a couple of older models as well. We also have support for a German manufacturer, Grohr, and we've recently had support for a French manufacturer, Meteor modem, added thanks to a contributor in France. So Radiosonde AutoRX is targeted at the Raspberry Pi platform, though you can run it on any Linux machine. Those guys that have got a Raspberry Pi 0W, it runs perfectly on that. And we currently have about 60 stations operating worldwide. In Australia, mostly Australia and Europe, though a couple in Brazil, funnily enough. So we do all of our reception using software-defined radio techniques.
So what software-defined radio is, it's just a way of getting RF spectrum into software. Unlike traditional radios, you don't really need any hardware demodulation or filters. So it keeps it really sort of simple, the hardware side of things, and allows you to sort of take that burden and do it into software. Gives us a whole bunch of features as well, because suddenly we can generate filters on the fly. We can capture a very large range of spectrum as well, which is what we use to do the Radiosonde detection. And basically it lets us search for the Radiosondes and then run our own demodulators to grab the signals out of them. So we're not tied to a specific Radiosonde. So SDRs have become really affordable since the RTL SDR came out. The RTL SDR is a TV tuner that someone found, I think, when they were making the Linux drivers, that it just provides the raw RF spectrum. to do in software. So as a community, there's been a whole bunch of tools built around that we've been able to make use of in this project to find radiosondes and decode them. So you can use SDRs for many applications. You can use it simply for just receiving FM stations, or you can use it to demodulate digital systems. In this case, we're going to use it for radiosondes. The other thing you might consider is what they call a preamplifier. It's just an amplifier that goes in before the RTL SDR to amplify the signals. This is useful if you have a very weak radiosonde signal that you sort of want to boost up and get a little bit more data out of. The other thing you'll need is a stock antenna. Usually the default one from the RTL SDRs that you can get, the little stubby magnetic one, it's usually good enough. It's not great, but it's good enough to get going to start with. If you want something better, say if you want to receive sondes from really far away or weak sondes or the like, you can build yourself a quarter wave ground plane antenna. There's lots of instructions online on how to build one, but basically it's a few pieces of wire at 18 centimeters long, sort of arranged in the picture there.
So the aim of the software-defined radio part of AutoRX is to go from something that sounds, here we go, is this going to work? Live demos, awesome. Something that sounds like that, to bits, then to packets. So that's transmitted using frequency shift keying. That is where we represent zeros and ones by two different radio frequencies, and they alternate very, very quickly. In this case, 4800 baud, lightning fast. We get about 1 telemetry packet per second, which is more than enough for tracking the movement of a device such as this. On the screen, there's what we call a waterfall display, power versus frequency versus time. The yellow blocks show individual packets. We decode that to bits, and we extract the actual data from those to produce something that we can actually read, latitudes and longitudes and altitudes and temperature and things like that. So here's a bit of a flowchart showing how AutoRX runs. So first off, we have all the kind of cool RF stuff, where we're getting those RF signals and converting them into bits. Then we have to actually find the radiosonde. So we observe the radiosonde spectrum, we take a long snapshot of it, we process it to produce a data set of power versus frequency. Using a pretty basic peak detection algorithm, we look for things that stand out above the background noise. These peaks are either going to be radiosonde signals or interference. We've got a lot of that around the place. Once we have a list of peaks, we have to be able to determine if that peak contains a radiosonde signal. Now, thankfully, radiosonde telemetry has certain characteristics that we can exploit to determine, to find out what these signals are. We know what the baud rate is. We know what the header of each telemetry packet looks like. So the sonde detector part of the signal processing chain does this FSK, frequency shift keying demodulation, and looks for these known headers. So it cross-correlates with a set of known headers. If we get a good correlation score, we've found a radiosonde. Once we've found it, we start decoding it. So we set up the appropriate demodulator and we start producing telemetry. This is logged to disk, but we can also export it to a range of mapping services on the web, such as the amateur radio packet reporting system, SomeHub, and other mapping systems that we've written ourselves. So AutoRX is written in Python 3, it runs as a service, you set it up. It uses systemd, I'm sorry, but it's okay, it works. And you can start it up and then pretty much ignore it. This is a bunch of log output. You can see it scanning, detecting, and then decoding. It's kind of hard to see what's going on from this log output, so I had a crack at doing a web GUI. Now, I should note that JavaScript scared the crap out of me for a long time, and then thanks to my co-workers, and hi, look, I've been shown that it's actually not that hard, and you can do some really cool stuff with it. So in this case, it's JavaScript, Flask, Socket.io, and Leaflet. It's a bit hacky, but it does the job. At the bottom of the screen, you can see a plot. This is the output of that spectrum analysis and peak detection step. So in this case, we found 2 peaks. As it turns out, only one of them was a radiosonde. So we've started decoding telemetry on 401.5 megahertz, and the basic telemetry data is showing up at the top of the screen. So latitude, longitude, altitude, etc. We also have a map showing where you are and where the radiosonde is. You know, voila, we can now track radiosondes. If you want to track more than one radiosonde, say you're in Europe and there's like 50 of them in the air at once, if not more, you can add more RTL SDRs and track all the radiosondes all at the same time.
So one of the places we output to is SomeHub. So SomeHub is a version of HabHub, and HabHub is a high-altitude ballooning tracking website. It's not designed for amateur radio or amateur balloon launches. It's not really designed for radiosondes. So we run sort of a proxy version of that where we swap in some filters that sort of target radiosondes specifically. So on the left, you can see all our radiosondes that we're currently tracking around the world, along with all the receiving stations on the map. So here we're looking at a balloon in Adelaide. You can see where you are with the person, and one of the key things to note here is you can see a prediction. This prediction is where the system believes the balloon may land. So we can use this online to track weather balloons, but potentially you might be offline and you might need to see where a balloon is and predictions for where a balloon is without cell phone reception, say if you're in the Adelaide Hills.
So I do high-altitude balloon launches with a group called Project Horus. We did the Penguin launch many years ago, and we've been doing lots of launches since then. Since we started doing this project, we've had an offline mapping system. This has been based around a bit of software called Aussie Explorer, designed for four-wheel drive mapping and showing topographical maps. It's, you know, it works. It's Windows only. It's closed source. It costs money. Well, that wasn't really good enough. So after doing the web interface for AutoRX, I had a go at doing my own mapping system. So again, Python, Flask, Leaflet, all that kind of stuff. It takes data from the AutoRX system, plots it on a map. Those map layers can be served up from a local tile server, so you can run entirely offline. As Michael's mentioned, we can use those weather models, the same ones that we saw earlier, to predict where the balloon's going to travel based upon wind movement at certain altitude layers. It's pretty accurate. It's surprising how accurate it is. Again, garbage in, garbage out. If you make a guess as to where the balloon will burst, if that's wrong, clearly your prediction is going to be wrong. But again, you kind of look at what happens over a few launches, and it works out pretty well. So on the map, we have the blue car. You are here. That's where your current location is. Again, you have to have a GPS for this to work, but that's pretty easy nowadays. And we can see where the radiosonde is as well. We can also see those predicted burst and landing locations. So if you want to recover the sonde, you should be driving to that predicted landing location at speed. Something I added recently was the ability to share your location with other users of the software. So, you know, a Challenger appears.
That's all.
Yes. So in Adelaide, it actually got so bad, we had to start up a mailing list because we had situations where people would arrive at the sonde landing site to find the sonde missing, and then they found out that someone else got there 5 minutes before them, grabbed it and ran off. So now we coordinate, and it's gotten a lot better.
Right, so some basic sort of chasing tools that you'll need. You'll need some sort of Yagi antenna and a radio, and this is to do a little bit of sort of direction finding if you can't find the radio. The other thing you'll need is a RTL SDR and antenna. So if you're using the mag mount that came with your RTL SDR, you can just stick it on the roof of your car, and it's that simple. You can create a bigger antenna and work out how to mount that on your car. The other thing you'll need is a laptop running AutoRX. The reason why we want to take AutoRX into the vehicle we're going to chase with is you want to try and get the GPS location the lowest possible point on the ground. If you are running it at home, it's likely that the radiosonde will be below your radio horizon and you won't see the last couple of packets it sends out. The other thing is you need the predictions because otherwise you'll just be driving in a random location. So you can either use SomeHub online if you think that cell phone reception is going to be great, or you can use the Chase Mapper application that Mark just showed us. The other thing is you're definitely going to need a vehicle. Like these things go out hundreds of Ks. So you can choose, if it's going to go far out, you can choose to use a car. If it's going to land nearby in your suburb, maybe a bike is a good option, and possibly even a Lime scooter. I don't know. It'd be fun. Yeah. So I talked about a Yagi antenna, and these don't have to be expensive. So this is my one. If it looks like it's tape measure, it's because it actually is, and it's irrigation pipe as well. So this entire antenna was built out of parts from Bunnings, with the exception of the SMA connector. That was, I think, like $2 off AliExpress. So these things are quite portable. They're very durable. You can just chuck it around and it doesn't really matter. It's also very compact in size, so it's not an issue just leaving it in the car. It's pretty hard to damage. Tuning and matching for all the RF geeks out there really doesn't matter because you're not transmitting on it. So it's all fine. So the reason why we need this is if the Radiosonde was to land in a field or somewhere like that, you sort of need to direction find to it because the GPS position you might get, it's still probably going to be a couple of meters off. And if it lands in a field, you're not really going to see the Radiosonde until you step on it. So you pair this up with a radio and you sort of just swipe around until you find the strongest signal. So there's some basic direction finding tips, like the signal might be behind you, so make sure you keep that in mind. So my first Radiosonde. So step one is don't just drive out. Run a prediction. So Radiosondes can go really, really far away. You want to find one that's going to be landing in a nice location. You don't want it deep in forest. You don't want it in the ocean. You want it to be in a very easy to get to sort of place. So don't go out for every single Radiosonde, run a prediction first.
So there's a really good online utility for this. So the same prediction engine that drives ChaseMapper and SomeHub is available online at predict.habhub.org, developed by Cambridge University Spaceflight, a high-altitude ballooning group, as it turns out. So you can set up a launch location, the parameters of the launch. So in this case, we specify a burst altitude, ascent and descent rates. And you pretty much watch a few balloon launches and figure out what those are. And we can work out where a balloon is going to go. So in this case, this is the launch tonight from that that launch site north of Wellington. And that actually looks pretty recoverable. So if I wasn't flying home tomorrow, yeah, that would be kind of cool, but not going to happen. So anyway, we can run predictions pretty easily.
Cool, so you've got a prediction that looks like it's going to be a somewhat successful recovery. You want to run AutoRX in your laptop, get that running. If you've got a Copilot, this is really easy. You can just hand them a laptop and say, here, have this. And they can also give you updates as to start driving this direction. It's really handy. So what you want to get them to use is check sonhub.org to see the predictions, or if you've got ChaseMapper, they'll be right there for you. And you want to start sort of driving towards the landing location. So when the balloon's going up, the prediction is going to be really rough because we don't know when the balloon is going to burst. You're best off waiting, sort of driving halfway out to where you expect the balloon to go, waiting for it to burst, waiting a couple of minutes to get enough data for a prediction for the final destination. And then you can keep on driving sort of towards that final destination, just keep iterating over that. So if you're lucky, you'll find the Radiosonde laying in the middle of the road, or it could be in the middle of a farm. Once you've found the Radiosonde, take a photo with it. The reason you take a photo and a selfie is you can tweet the bomb with the serial number. We love doing this. I think it's great, sort of sharing around our experiences. The other thing is these Radiosondes, they'll take you in all sorts of different places. So one day it might be a suburb you haven't been to before. Other times it could be a nice pretty field like this one here. This is an example of like why you need the direction finding, the Yagi antenna, the radio to do that. Because when I took this photo, I didn't actually know where the Radiosonde was. We were still sort of walking around looking for it. So it can be very hard to find them if you don't have that direction finding. This isn't the only place they'll end up though. You could get nice rocky mountains like this, or you might end up with suburbia. So the one on the left here, it was strung across the house. The people living there found it quite interesting, somewhat amused. The one that Geordie is trying to get to there with our 10-meter squid pole, That one landed in a tree, and the tree was high enough and close enough to our place that we could actually still receive the packets for another 6 hours. Two other people tried to retrieve that sonde, but we just happened to be the ones with a big long stick. So, recycling radiosondes. So you got the radar reflectors, that's this big shiny thing here. Reflects light really well, and radio waves, very shiny. You've also got string and rope, because these are tethered to the balloon. It's okay string, the rope is probably much better. We didn't bring any of that, unfortunately. Good for tying things up. Got batteries, TV remotes, love these things. They're lithium batteries, and they've only really been used a little bit, maybe 30% or so. So you can put batteries that have been to like the edge of space, in your TV remote. And there's this like microcontroller or something, I don't know. But Christmas decorations.
That's my living room, by the way, on the right-hand side. I had way too many of these things. So reflashing the RS41 is really, really easy. Really handily, all of the pins you need to flash the STM32 are broken out to the expansion header. No bodge wires, no pogo pins. You just get the appropriate plug, or just use jumper leads and plug it into an ST-Link or a Chinese clone, which costs $5 on eBay. And you use OpenOCD or whatever you want to and flash it, and away you go. It's great. There's a bunch of example projects on firing these things up on GitHub. So the first one there is a fox hunting beacon. So in amateur radio direction finding, which is a competition sport, by the way, we hunt radio transmitters like Radiosondes sometimes. This one's slightly modified. It's a bit black and it's sticks to things. So you can stick it to road signs and stuff like that, and it makes it really hard to find at night time. It's awesome fun. So we also have the GPS positioning beacon software. This is most important to me. This is where I use these Radiosondes. So as I mentioned before, I'm a part of Project Horus, and we've been doing balloon launches since 2010. We've done 51 launches so far, including 2 at LCA 2012, the red balloon out in the field, out in front of the main conference venue, if anyone remembers that one. As of mid-2018, we are now using these RS41s as our primary tracking beacons. We even went, it's arguably cheaper and way more fun than just building one. We just go out for a drive and have find bakeries once we've found the balloon. It's a thing. Anyway, David Rowe of Codec 2 fame and I designed our own modulation scheme to use with these. It has significant performance improvements over what we've been using before, about 4 or 5 times better minimum detectable signal. And there's more on that at the GitHub link there. We've been using this for quite a while now.
So basically, these are just a general purpose STM chip. So basically, any STM32 project that will fit in the 64K of flash and 8K of RAM will work with these things. That gives us a few options for other things. So if you want a very expensive or maybe free wireless thermometer, depending on how you value your time and fuel, that's one option. Some reverse engineering is required to make the thermometer work, so good luck with that. Otherwise, you could use it as like a smart home device, potentially. A lot of smart home devices seem to transmit on 433 megahertz, and these will quite happily do that. This has a GPS in it, so it makes sense to use these for projects that require GPS. The one that comes to mind is the Open Glider network. Some modification will be required to make it transmit on the 900 megahertz that's required for that, but it should be quite doable. We just need someone to do it. The other thing that these Radiosondes have that you can repurpose is the sticker on them. The sticker says, "Do not burn or incinerate." It's great for putting on your laptop. The other thing is the data. So we track all this data and we get it into SomeHub. We also put it into Elasticsearch. So we can pull that data out, we can put it into different systems, we can make pretty graphs with it. One thing that I really want to see is, can we generate our own weather and wind models? I'm not a data scientist, so I have no idea how to do this, but you're more than willing to use our data to try and achieve that. It'd be really good if we could use the data we're getting for prediction modeling. So one thing is, when we're running the predictions, we're using basically the wind model from 12 hours ago. It would be amazing if we could process that data as the balloon's going up, so when we run the predictions for when it bursts, we could get more accurate landing zones. And cool graphs, I guess, you can use the data for, which is good. So at the moment, unfortunately, we didn't quite get to over 9,000 Radiosondes. We're really hoping, like throughout the week, we're checking back each day to see if we would reach it, but not quite. But we do have 60 receivers, which just blows my mind that so many people are doing this. And I want that number to grow and grow and grow. So just like a quick, huge thank you to like all these people that are running AutoRX stations already. And this isn't just an excuse to generate a word cloud, but these people have been tracking lots of Radiosondes for quite some time now, and you too could get your name on a slide like this if you were to set up your own AutoRX. So how can I get started with this? So the easiest thing is like setting up a receiving station. You only have to go outside to set up the antenna, and then the rest of it is just software inside, so it's nice and easy. Once you've got that, then it's quite easy to take that setup, apply it to your car, and then chase a Radiosonde. And it's really good fun. It's a bit of a thrill getting into chasing Radiosondes. If you're not up for that, you can help us reverse engineer the hardware. So there's a few bits and pieces that we'd really love to get going on it, which is like the RFID, would love to understand how it works, and also reading the sensor stalk, which requires a bit of sort of knowledge about how the analog circuits work. Sort of to add to that is, in theory, we can do an attack on the STM32. It's got like a cold bootstepping attack where we can sort of dump the original firmware. But we haven't been able to succeed with that. So if you have any knowledge about doing the cold bootstep attack, please come down to the front afterwards and you'll receive your complimentary RS41. You can also just come up with some cool software for it. So if you're if you're like a STM32 developer, you can just get started and start developing for these. If you're a data scientist, you can use our data. And finally, you can build a radar reflector sculpture because that's cool.
So thanks for listening to our talk. Given we've got a couple minutes and we have the break immediately afterwards, I'm just going to share a short anecdote which occurred this week. So earlier this week we saw, it's actually a little bit earlier than that, we saw a Radiosonde launch from a tracking station in Finland, which had a really weird serial number. So all these Radiosondes have a serial number, and it actually means something. The R indicates that it was built in 2019, and the other numbers indicate that it was built on the 7th of February. And it launched 3 days later. Now, shipping isn't that good from these companies, right? So what's going on here? Well, we have a complete track of the flight path, or pretty close to it, so we can have a look. Where did it come from? So we zoom in a bit, and it came from near Helsinki, and we didn't quite get it from launch. The tracking station was about 100 kilometers away. It got it at about 1 kilometer up, but right in the middle of this map is Vaisala's headquarters. And there's their automatic Radiosonde launcher. Hi, Vaisala, we can see you testing. That's all I got. Cheers. Okay. Run.
Do the organizations that launch these weather balloons care that people are going out in fields and picking them up? Because presumably they spend money on it, and since the company seems to have a monopoly, a lot of money, I would guess, if they have a monopoly.
Okay, so I can answer this one. The short answer is no. They don't care. So what happens is when these very, very fragile sensors hit the ground, they often break. This just pulls apart very, very easily. They are single-use devices. They might be very expensive single-use devices, but they are single-use devices. The exception for that is the ozone sonde package. They cost a lot of money, a couple $1,000. and they want those back, you get 50 bucks. Doesn't quite cover your fuel. Not quite, anyway. Not anymore. But yeah, these are all single-use devices. The Bureau of Meteorology are aware that we do this. They don't care. They think it's awesome. So yeah, because they don't track them after burst, by the way. They don't track them down to the ground.
There's also some countries do have a bounty for them. From what I've heard, it's not much, but at least it's something for getting it out of the environment.
Next question. He's running that way somewhere.
So most GPSs have a maximum altitude that they quit working at, or at least most of them do. So this one seems to go to 50 kilometers, which, if it's this, is it the 6 or the 6M?
Okay, so all the U-Block series chipsets work properly. They actually adhere to the COCOM limits, which says you cannot go, I believe it's higher than 50 kilometers and faster than some particular speed. The idea is it stops you from building missiles out of them. However, if you are under 50 kilometers and going slower than that maximum speed, there's no reason why you can't get GPS lock. You have to put the GPS into the right mode so it accepts the fact that it's at 30 kilometers altitude and doesn't, fritz out. But it's really easy to do. These U-Blox GPSs actually work fine, and you can configure those settings. So yeah, they're perfect for high altitude balloon launches.
Have you tried plotting all of the recovery sites on a map to see if it clusters?
I have. It's not in this slide. I can show you afterwards. They're spread all over the place. Any other questions?
Two things. So before anyone was collecting these, and still when people don't collect them, they're just hundreds and thousands of them are just littered?
Correct.
Yep.
Wow.
So whenever we go and recover these things, particularly in farmers' fields, more often than not, the farmer has encountered one of these before. They've found them stuck in a fence, sprawled across a field, which gets caught up in their harvesting equipment. We've had, in the Adelaide Hills, we've had farmers with cattle who have actually had cows die because they've eaten the latex balloon and it's blocked up their guts. So yes, this is a thing. It's been going, look, again, we've been launching Radiosondes for many, many years, and they land all over the place. And know that people don't recover them, except us.
Then one other thing, I was looking at the tracker online. There's no activity in the US. Are they launched in the US?
We currently don't support the Radiosonde model that they use in the US. We would love some samples so we could add support. I actually have a couple which I haven't gotten around to working with yet. Again, we require receiving stations, essentially.
Has anyone programmed drones to go chase them down and pick them up and bring them back to you?
It's funny you mention that, actually. Not me. I should say not me. The classic example there is Radiosonde has landed in a field somewhere, and we don't really want to go across the fence. We'd like to have a drone that goes out with a claw and picks it up. The problem is that the Radiosonde might be here. This might be 50 meters away. And so you pick up the Radiosonde and suddenly you have to deal with 50 meters of string and this thing at the end of it, which acts like a big land anchor. It's totally possible, but no, we haven't actually done it yet.
Do you know much about the flight paths with aeroplanes and things like that?
Good question. You want to cover this one?
Yeah, so when I looked into this, at least for Melbourne Airport, there is a process, because they launch from the airports, they basically clear with ATC first before they launch it. Because it travels so quickly up the atmosphere, it's out of the flight path very quickly. When it returns, it doesn't spend a huge amount of time in the flight path, and sort of the chance that it'll be involved in some sort of air incident is very, 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 very small.
And the actual impact of that is pretty low as well. Most jet engines can take 4 kilos of debris, think bird, going through them. This is really not that much.
Any other questions? Oh, thank you very much for a really interesting presentation.